Hello grade 11s and welcome to this lesson about the difference between real and ideal gases. In this series, we have seen that pressure is inversely proportional to volume and pressure is directly proportional to temperature. These relationships are summarized in this equation. We have also seen that pressure is directly proportional to the amount of trapped gas. We can include the factor into the equation like this. We have also seen that this equation can be rewritten as the universal gas equation. So far, we've taken these proportional relationships and therefore these equations to always apply to all gases. In fact, there are some situations when these equations won't work. This is because gases are not as simple as our model. We can call the gas which our model describes an ideal gas. Remember that in our model, ideal gas molecules jump around and fill the container they are in. In this model, all the ideal gas's volume comes from the spaces between the molecules. The molecules themselves take up no space at all. Also, although particles in the solid or liquid phases do attract one another by intermolecular forces in an ideal gas, the particles do not exert any intermolecular forces on one another. These two simplifications make our model and equations easy to use, but they are not actually true. Let's start with intermolecular forces between gas molecules. Our simplified ideal gas model says there are none, but real gases do have intermolecular forces. Under most conditions, these are so weak we can ignore them. But under some conditions, these intermolecular forces are strong enough to cause the real gas to behave very differently to an ideal gas. At low temperatures, the gas molecules move very slowly and so stay close to one another. This strengthens the intermolecular forces, which eventually cause the gas to change phase. Notice how the water vapor in this simulation changes to liquid water and then to solid ice as the temperature drops. Of course, the gas equations don't apply to liquids and solids. Remember how the learners extended their graph line to predict the temperature at a pressure of 0 kilopascals. We call this temperature 0 Kelvin or absolute zero. At this temperature, gas molecules have no kinetic energy at all. Actually, it would be impossible to cool a real gas to 0 Kelvin because it would change phase and not be a gas long before 0 Kelvin. This graph line shows the direct proportion between pressure and temperature for an ideal gas. This graph line shows that at low temperature, a real gas changes phase, so the direct proportion ends. Now let's look at the other simplification of our model. In an ideal gas, the molecules themselves have no volume. Obviously, this is not true. A real gas's molecules do have some volume. So at a certain pressure, a real gas's volume is actually bigger than what the ideal gas equations predict. Under most conditions, the spaces between molecules are much larger than the sizes of the molecules themselves, so that the error from the simplification is negligible. But at high pressures, the gas is compressed so much that the volume of the molecules are significant compared to the spaces. So at high pressures, a real gas has significantly more volume than an ideal gas. Let's summarize the conditions under which real gases differ significantly from ideal gases and why this is so. Real gases differ from ideal gases at low temperatures because at low temperatures, gases change phase, and so the gas laws no longer apply. Real gases also differ from ideal gases at high pressures. This is because at high pressures, the volume of the molecules themselves becomes significant and so can no longer be ignored. Now let's discuss the gases which behave most like an ideal gas and why this is so. So far, we have only investigated the effects of these variables on gas behavior. temperature, volume, pressure, and amount of gas. We have not discussed the effect of the type of gas on its behavior. This is because, in ideal gas theory, all gases behave the same way. However, some gases behave more like an ideal gas than others. Gases with weak intermolecular forces and molecules with a small volume behave most like an ideal gas. The noble gases have the weakest intermolecular forces. Helium is the noble gas with the smallest molecules. So the noble gases, especially helium, behave most like an ideal gas. And that brings us to the end of this series. Don't forget about the task video. Also check out other videos in this series and look at the Mindset website at www.mindset.co.za/learn. Goodbye.